energy has two general forms, kinetic and potential. Kinetic energy is the energy of movement. It is, for instance, gases moving around a room. In this room we're sitting in now and where you're sitting, there are gases moving at probably about 400 miles per hour. We don't feel that because they're so small. But that energy that they carry is kinetic energy. Now, the other type of energy is called potential energy, and that's energy that's stored in, that's one definition, but a better definition of potential energy is energy of position. For instance, when you're on a roller coaster and you're at the top of the hill, right when they pull you up, when you get on the ride, when you're at the top of that first hill, you have a lot of potential energy, which means you have the capacity to do a lot of work. So as soon as you go over that first hill, all your potential energy is then converted into kinetic energy as you move through the ride at high speed. Now in chemistry, kinetic energy, like I said, can be considered the movement of molecules or atoms. Potential energy can be considered the energy that's in chemical bonds. There's stored energy in a piece of coal, charcoal, and gasoline. We want to know how much energy is stored and how we can use that energy. So the key to that in calculating that energy is understanding that when you break bonds in reactants, you have to put energy in. That requires energy. Water isn't just going to break apart spontaneously. It has to have energy put into it. But when you form the products, you get energy back. So product bonds are, when they're formed, you release energy. So how we do that in chemistry is we look at the Lewis structures like we've drawn before. So if you look at this balanced reaction, it's two water molecules give you two hydrogen molecules and oxygen gas. So if we draw out the Lewis structures, you'll see that there are two water molecules. So there are four OH bonds, and we get two hydrogen molecules formed and one oxygen molecule formed. Now, I wouldn't expect you to know these numbers in red here, but these are the energies it takes to break these bonds. So an oxygen-hydrogen bond takes 112 kilocalories, and I'll clarify what a calorie is in a little bit here. When you form a hydrogen bond, you get 103 kilocalories of energy back for every mole. That's what this kcal per mole means. For 1 mole of hydrogen, you get 103 kilocalories back. When you make 1 mole of oxygen gas, you get 119 kilocalories back. So the energy change in a reaction is simple to calculate. All you need to do is add up the energy it takes to break all the bonds. In this case, we're breaking 4 OH bonds, so that's 112 times 4, which is 448. And you get back twice the energy of a hydrogen-hydrogen bond, 103 twice, plus the energy of an oxygen-oxygen double bond. Those numbers add up to 325 kilocalories. So the difference in those energies is the energy change of this reaction. And later on you'll see that we'll call that the change in the enthalpy. Right now, just think of it as the change in energy of the reaction. Are we giving up energy or are we consuming energy? So on this next page, actually I want to go to that later. I just want to finish up this problem here. So if we look at this reaction again, that 123 kilocalories that I just calculated would be on the left side of the reaction. We call that an endothermic reaction. Heat has to be put in. You can think of this as heat. You have to heat up water, or you can give it a jolt of electricity. That could supply this 123 kcals of energy that would cause it to break apart into 2 hydrogen molecules and 1 oxygen molecule. But what I want you to understand is that when energy is on the left, or heat, that it's called endothermic. Energy is absorbed from the surroundings. The surroundings is everything outside of the reaction. That's us. So in contrast to that, you can have what's called an exothermic reaction, which is an energy that releases heat. Notice the heat is on the right side of the reaction here, and in the decomposition of water, it's on the left side. I haven't given any specific number for the heat of this reaction. It doesn't really matter at this point, but you'll see that sometimes it's heat's on the left and sometimes heat's on the right. Endothermic, exothermic. So, for instance, this is the reaction we've talked about many times. The combustion of gasoline, or octane, requires 12.5 moles of oxygen. It gives you 9 moles of water and 8 moles of carbon dioxide plus energy. We can calculate that, and I may do that in another video where you can actually add up all the bonds broken and add up all the bonds formed. It's somewhat tedious, but it's not that difficult. And you can calculate how much heat you'd get out. Engineers would be interested in that, and so would gasoline companies, to make sure they are using fuels that are efficient. So we will calculate that later.